I want now to explain a few applications for table constraints so that when you see a similar application, you can think about maybe I should use a table constraint for my model in constraint programming. So the application is a very toy example, which is a puzzle matching, an edge matching problem in a puzzle. So this is a famous puzzle that was called Eternity 2. And for the story, this puzzle was, so the organizer who invented this puzzle promised to offer a $2 million award for people who could solve this edge matching puzzle. And of course, it was never, it was not, nobody was able to solve it because it was really, really hard to solve. But a possible way to model this puzzle in constraint programming is to use table constraint, as I will just explain now. So this puzzle is a 16 by 16 grid. Okay, and you have, of course, 16 by 16 different pieces. And every piece that you place next to each other should have edge matching. So a piece looks like this. So a piece is divided by 4 different shapes and colors. And if you place 2 pieces next to each other, they should match. Okay, the color should match, and the shape should match. So this is a possible solution for a 4 by 4 puzzle here. And you see that on every edge here, they match, right? They match next to each other. And the goal is to find which piece you should place in every location of the grid. And of course, with satisfying the rules that every piece of the puzzle that are placed next to each other, they should match in color and shape. So how to model this puzzle in constraint programming? One possible way to model this puzzle is to introduce one variable here for all the different positions on your grid. And this variable will contain the identifier of the piece that you will choose for placing at this specific location. So for instance, I11 would contain the identifier of the piece that you will place in this position 1, 1 on the grid. And of course, here I've got a 4 by 4 grid. So the variable goes, identifier variables goes up to I44, okay? For the identifier of the that would be placed in position 4, 4. But this is not the only variables that I need here. I will also introduce one variable to represent the identifier of the color shape on every edge of the position. Okay, so that will be the up edge, the left, the right, and the down edge here. And you see that I also introduce one variables for each of them. Since in this puzzle I've got overall only 4 different types of shapes and color, my domain will be from 1 to 4. And since I've got 16 different pieces, all of them are different, I've got a domain from 1 to 16 for all the identifier variables. Okay? And then, as you can expect, we will introduce a table constraint to enforce the rules of the game. And also, we will use table constraint to enforce that the identifier assignment that you will decide here corresponds to a real piece of your problem, of your instance. Okay? So these are all the pieces of your problem. So for every piece that I have here, of course, I can decide to rotate it by 1, by 2, or by 3 different rotations. Okay, by 1 quarter, by 2 quarter, by 3 quarter, or no rotation at all. And this is what I will use to fill in my table. So I will introduce a number of entries in my tables that will contain tuples with 5 entries. Okay, this will contain the up color shape, the right color shape, the down color shape, and the left color shape. And this is the identifier. Okay, and of course I need 4 different rotations, as I explained. So this is 1 rotation. If I don't rotate it at all, I would have here, you see that the identifier is 9, then up is 3, right 3, 2, 2. So this is one possible entry, is 9, 3, 3, 2, 2, if I don't rotate at all this piece. If I rotate it by 1 position, by 1 quarter, like this, I would get another entry. Okay, this is also a valid combination for this piece. Okay, and now you see that the 3 is up. Then I've got at the right the 2. At the bottom you've got the 2, and then you've got the 3 left. Okay, then I can rotate it by 1 more got another entry in my table, and then the final rotation is this one, and I've got another entry, and still this corresponds to identifier 9 here, okay? So you will introduce one entry for every possible rotation, which means that you have 4 different entries in your table for every identifier. You will do that, of course, for all the 16 pieces, and so overall you will have, okay, this is for this piece, you've got 4 additional entries. You do that for all of them, okay, and so in the end you've got, as you can expect, you've got a 16 by 4 entries number of rows in your table that would correspond to every piece multiplied by every possible 4 rotations that you can get, okay? Okay, and so these are the tables, and of course you also need a constraint to state that all the pieces that you would choose are all different. You cannot reuse 2 times the same identifier, and this is why you also get here an all different constraint here between the identifier variables to make sure that you don't reuse 2 times the same piece. Okay, this is forbidden. All of them are different, and you know that by construction of the problem. And of course, because you want to use only valid pieces of your puzzle, you also enforce that with the table. You say, okay, this is the big table of pieces that you have constructed. So this is the Java array that contains all the possible combinations that correspond to real combinations of and rotation of real pieces. And you say that every variable, so let's take this one, I33, then this one is 1, okay? So all these variables, they belong to a possible combination of the table of your game, okay? And of course, you will do that for all the possible here positions in your board. And this will make sure, together with the all different constraints, that you will only place valid pieces of your puzzle, and all of them will be different. But that's not all, of course. You also need to enforce that you have edge matching constraint. And this is enforced here by reusing. You see that I'm sharing the variable between every 2 adjacent pieces. I use exactly the same variable. So this will make sure that I have edge matching puzzle. Okay. If you don't do that, if you duplicate the variable on the left and on the right for every edges, then you need to enforce that you have the perfect equality here. But here I avoid that by reusing the same instance variable. Okay. And so since I'm sharing the variable